Every engineer starts out with these beautiful, elegant equations and perfect models. But the real world? Oh, it's messy, it's unpredictable, and it's exactly where those perfect theories have a nasty habit of breaking down, sometimes in a really big way. So why do designs that look absolutely flawless on paper fail so hard in reality? And more importantly, how do we build things that don't?
All right, let's get into it. First, we're going to tackle that massive gap between theory and reality. Then we'll pinpoint a huge unresolved problem that trips up engineers all the time. We'll also take a hard look at the so-called safety factor and ask if it's actually making things worse. After that, we'll explore a much smarter design philosophy, walk through a super practical checklist, and figure out what really separates a good engineer from a great one.
Okay, so let's start with this classic battle, right? The pristine, clean world of the textbook versus the absolute chaos of the real world. This is the question that keeps engineers up at night. You can calculate everything out to the fifth decimal place, but reality? Reality always finds a way to throw a curveball that your original model just never saw coming.
And this, right here, this is the heart of the problem. See, in class, you learn these beautiful, clean principles. You learn Fourier's law for heat transfer, but in practice, you get fouling, this buildup of gunk that completely messes up your surfaces. You rely on Bernoulli's equation for how fluid should flow, but then you face flow maldistribution, where the fluid just decides to go wherever it wants. Your ideal models assume everything is perfect, but reality hits you with corrosion and cavitation that literally eat away at your equipment. And my favorite, we love to design for steady, stable operation, but the most brutal stress a system ever sees, that happens in the chaos of startup and shutdown.
So out of all these real-world villains, there's one that really stands out from the pack. It's a problem so common, so difficult, that it's been called a major unresolved issue in its field.
Yep, that's the one. Fouling. It's basically the deposit of solid, insulating material onto heat transfer surfaces. This quote tells you just how big of a deal this quote-unquote gunk problem really is. You could call it the silent killer of efficiency in, countless industrial processes.
And this slide just brilliantly illustrates why it's such a nightmare to solve. See, fouling isn't just one thing. It can be minerals dropping out of water, little particles just settling down, chemical reactions creating solids, plain old rust, biological slime, or even freezing. It's like a multi-headed monster, and a solution for one cause might do absolutely nothing for another.
So if we know fouling is going to happen, the logical thing to do is just design for it, right? Add a little extra capacity, a safety margin. But what if that very instinct is a trap?
This is the standard playbook. It's what we're all taught. You expect some gunk to build up, so you oversize the equipment by adding what's called a fouling factor. It's basically a built-in safety net, meant to make sure the thing still works even when it's dirty. Seems responsible, right?
And here's where things get really counterintuitive. Could our attempt to solve the problem actually be making it worse down the road?
This just nails the paradox. When you make a piece of equipment, like a heat exchanger, way too big, you can actually create the perfect conditions, like slower fluid speeds, that speed up the very fouling you are trying to prevent. Your fix becomes part of the problem. It's wild.
This is exactly why we need a total shift in our thinking. Instead of just slapping bigger safety margins onto our perfect ideal models, we need a design philosophy that actually embraces the messy, irreversible nature of the real world from the get-go.
Now, this new approach has a pretty fancy name: Entropy Generation Minimization, or EGM. Okay, that sounds really complicated, but the core idea is actually simple. It forces you to build realistic models from the start. It combines thermodynamics with the nitty-gritty details of fluid flow and heat transfer to account for all those real-world imperfections that create waste, or what scientists call entropy.
So why does this matter? Well, because the goal isn't just to make something that works on paper. The goal is to design a device that wastes the absolute minimum amount of energy while doing its job, all within the real-world limits of size, cost, and time. It's all about being as efficient as possible in a system that you know is not perfect.
Philosophy is awesome, but we're engineers. We build stuff. So let's turn this mindset into a practical, hands-on checklist of critical problems that designers, honestly, they just overlook way too often.
So we've talked a lot about fouling, and it's a big one, for sure. But it's not the only gremlin in the machine. There are a few other operational troublemakers that can bring a perfectly calculated design to its knees. And honestly, just knowing to look for them is half the battle.
So here it is, a simple 4-step reality check for your designs. We need to handle uneven flow. Make absolutely sure we can get gases and liquids out of the system the right way. Plan for the stresses of startup and shutdown. And finally, set constraints that are actually achievable in the real world. First up, flow maldistribution. And this is a huge one. It's kind of shocking, but in a standard shell and tube heat exchanger, as much as 60% of the fluid isn't even touching the tubes. It's not doing its job. It's just taking shortcuts through bypasses and leaks. And this doesn't just tank your efficiency. It can cause total failures, like zones where gases build up or even freeze-ups in cold weather.
Okay, next, venting and drainage. It sounds so basic, but it gets done wrong all the time. You've got to vent those gases that can build up and just cripple your system. And when you're draining liquids, a really common mistake is to size the drain pipe for full flow. Don't do that. A great rule of thumb is to size the pipe assuming it's only about half full. This makes sure there's always an air gap at the top, letting liquid drain smoothly, like water over a tiny dam, and it prevents it from backing up and flooding everything.
And this is huge. Your system is going to spend most of its life running at a steady pace, but it's going to face its biggest tests during startup and shutdown. Those rapid changes in pressure, in temperature, they can cause stresses that are way beyond the normal operating conditions. If your design can't handle those intense moments, it's a failure just waiting to happen.
And finally, let's get really concrete with some realistic design constraints. Think of these as guardrails for your design. For anything involving boiling or condensing, try to keep your pressure drop to less than 10% of the operating pressure. It's a great guideline. And for liquid flow, you have to manage its speed. If it's too slow, gunk builds up. If it's too fast, you literally start eroding your equipment away. These numbers you see here, they're kind of the Goldilocks zone, the just right speeds to give you a safe, long-lasting design.
So all of this, it brings us to a much bigger idea. See, being an engineer isn't just about getting the numbers right. It's about wisdom, it's about foresight, and it's about understanding the deeply imperfect world we're building things for. Which leads us to this final thought. We've all got incredibly powerful software that can solve complex equations in a blink. So, what's the real difference between a calculator and a great engineer?
And this is the answer. A calculator lives in a perfect theoretical world. A great engineer lives in reality. They anticipate the gunk. They anticipate the uneven flow. They anticipate the shutdown shocks. They use their experience and a deeper design philosophy not just to solve an equation, but to build something that actually works in our imperfect, irreversible world. And that makes all the difference.